Okay, so let me give you some, this is the outline of the presentation. So this is actually will give you a brief review on all the different types of maximum power point tracking algorithms. And then we look into the partial shading conditions and the effects of the bypass diodes, and then look into our proposed method, which is the DE methods, and then how it performs. And then we will present some simulation and experimental work, and then we end up with the conclusions. Okay, like we see the photovoltaic systems nowadays, it has a large or wide range of applications, ranges from our small homes, and it becomes we call PIPV, you know, it's building integrated photovoltaic systems. It becomes a part of the building structure. And then we can see this in the second picture, which is a stadium, which is fully covered by photovoltaic systems. And for example, for aerospace, it's been used since the 60s. Since the 70s, aerospace applications. And then you can see here in other locations where it is used in bridge, for example, in remote areas like North Poles and desert areas, also the photovoltaic systems is increasingly useful in many locations. This graph, which has been from the National Renewable Energy Laboratory in the US, is showing the trend on how the PV systems or how the solar cells improves from 1976 when it was first introduced till today, till 2020. What's the trend here? You can see the trend is increasing for all the types of solar PV solar cells. This means the improvement of efficiency. And you can see here, it's already recorded of 46% efficiency for multi-junction solar cells. Okay, so most of the solar cells actually is experiencing an increase in terms of efficiency performance, and this goes throughout all the types of solar cells. Means this gives a hope that one day maybe we can reach to a breakthrough of solar cells. Maybe they can reach to 50% or 60%. Even with this current efficiency, which is the commercial efficiency, it's around 18 to 20% efficiency. We are already reached to the break even of the cost of electricity that generated from the PV compared to the electricity generated from the conventional sources. All right. And also this from this graph also, it gives us an indication that we are not allowed to lose any amount of power after the PV panels, because the PV panels, relatively the efficiency is quite low. Like I said just now, the commercial solar cells, it's around 20% of efficiency. So we are not allowed to lose any power. So all the electrical systems that is being used after the solar cells should be efficient almost 100% or 100% efficiency. So we cannot lose any more power. So this is just to maybe review on the characteristics. So these are very common characteristics. So we know that the PV output changes depends on the watt per meter square received. So this is the current, and we call it the IV curve. Okay, at a fixed temperature, for example, here 25. Also, the temperature has an effect on the power produced by the cells. As the temperature increases, the open voltage drops, and also there is a little bit slight increase in the current. However, the overall power will be reduced, and this is what we call the IV curve and the power curve. And in at each point of time on the IV curve, there is only one maximum power point. We call it the MPP, and that's represents the best operating point of the photovoltaic system, which gives you the maximum current and the maximum voltage, and which gives you in return the maximum power. So we need to operate our systems always at the MPP. All right, so that's and these few factors which influence the power. The solar irradiance level, which is, as I see here, it's clearly shown in this curve here. Surrounding temperatures, the temperatures affect the performance of the PV panels, and then also the load dependence. Sometimes the load the load also has an effect on the output power on the PV panels. Okay, what's the role of MPPT? I think the maximum power point tracker, which is a commonly used term, and the role of the MPPT is to track the maximum power. Remember just now when you see there is different IV curves, also there will be different power curves. So the IV curve here for 100 watt per meter square, 800 watt per meter square, and 600. This will give you different power curves. And these different power curves means will give you different MPP. And this keep changing. If there is a cloud, there is what we call shading, there is whatever. So this will keep changing. And that means the maximum power point tracker should be able to track the maximum power. And then the same thing goes, this is for the temperature increase. The temperature also increase will result in a different power curve. And different power curve means will result in different maximum power points. And the algorithms should be able to track these weather-dependent changes. And this is just to show you an example here. This is a day where we have the PV power in kilowatts, and this is during a cloudy day. You can see how the fluctuations happens. So this shows the effects of clouds on the output power produced from the PV panels. Whereas we can see in the similar systems that with the clear day, you can see the effects. You can see it's almost uniform amount of power that can be generated throughout the day. Yeah? Okay, so this is to show the impact of clouding. So what is actually photovoltaic systems? Actually, photovoltaic systems, it consists of the PV panels, and then you have this converter, which is a DC-DC converter. This is a cyclic converter in this case here, and then we have the load. The load can be either a DC load, which can be a DC motor, can be a lights, can be whatever, or can be an inverter. Can be an inverter, and that inverter will be connected to the grid or to the load, to the AC loads. So we have a DC-DC converter, okay, and this DC converters, and then we have the load, and then we have here the controllers, which is actually based on the input from the PV panels. We have controllers, and then this controller will generate the switching or drive the IGBTs or the MOSFET used. So a brief review on what are the current or methods of tracking MPPT trackings. There are quite a number of them, which has been reported in the literature. We can classify them into two new categories, which we call them a local search space or global search space. And the local search space, we have quite a number of them. We have the fractional open circuit voltage, fractional short circuit voltage, short circuit current, incremental inductance, P&O, fuzzy logics, and non-matrix. For the global search, we have mainly the artificial intelligence, which is the P&O, the DE, which are direct, modified P&O, and modified incremental. And there are quite a number actually. Recently, new methods have been reported in the literature. Okay, let's start with the first one, which is when we take the local search methods. So the local search methods, there are a few of them. For example, the first one, which is the fractional circuit open circuit voltage. This is a very simple method. We know that at each point of time, we have this is the VOC, okay, on this curve, and this is the VMP. So the location of the MPP, usually it is around 0.7 to 0.8 of the VOC, means within this region. And that's basically this method is all about. So we have VMPP equal to KVOC. So we need to set what is the value of K, and this K actually gives us what will be the MP. When we know the VMP, then we can determine what will be the IMP. Very straightforward. So based on experience, based on practical implementation, this will be something like this. But this cannot be worked, for example, when we have multi-peaks or partial shading conditions. Same things for fractional short circuit current. Also, it's IMP equal to K times IC. For example, at any point here, you have certain current, and then that will determine the voltage. So both algorithms need only one sensor. Either it's a voltage sensor or current sensor. So in terms of cost of implementation, it's a cheaper. Then we have the P&O methods. The P&O methods is based on this curve here. You can see this curve, usually this is the power curve. Okay, you have the voltage, you have the power, and then there could be the MPP at any point of this curve. But usually this is the MPP, which is the peak one. So this is a possible starting, and then you check the increase in in a power. Is it positive? If the power, we measure this, the next value of power. If it is positive, then we move until it becomes negative. Means we have to move in the opposite direction till we get the change in power 0. When we change the power, 0 means actually that corresponds to the MPP. Yeah. This is one of these advantages of this method of the P&O. It may track inaccurately under fast changing. Means if the change in the power is quite fast, maybe it will give you the wrong information. So this is one of disadvantages of this method. We have the incremental conductance also. It's based on the similar. So it divides the power curve into 2 regions, which is the left-hand side and the right-hand side. And this is the formula which is dP over dV equal to 0. Which once this one is satisfied, means that corresponds to that. We have the fuzzy logic. I think most of you maybe knows about it. It's based on rules, and based on these rules, we derive based on the voltage and current, and we can get out the duty cycle which supplies to the converter and transformer. We have the neural networks also. It can be also used. This depends on the number of layers. The more layers, the more accurate, but maybe it takes a longer time to track the maximum power point. Both algorithms are highly dependent on user experience. Means how you design your hidden layers and then how you derive the rules for the fuzzy logics to track the maximum power. And these are the references, some of the references which can be useful for people who are interested to use the two methods. The PSO, the global search, we have the PSO, which is quite very commonly, recently used quite commonly. The advantage of these methods is using the particles, as you know, for the PSO, the people who are using it. The accuracy of the algorithms increase with the number of particles, but we have to limit the number of particles to use the speed. Okay, sorry, to increase the speed. Okay, but at the same time, searching may take time. So we have to balance between the number of particles and the accuracy. We have the dividing rectangle, which is direct. It's also another method which can also used. The algorithm may miss this global entity if the wrong selection will be done. So from these methods. Okay, what is the impact of partial shading? I don't know. It's maybe if you are aware. The partial shading actually when a part of the PV panels is being shaded and the other part is not being shaded. Okay, as you know, the solar cells in each panel is connected in series to increase the voltage. Okay, and once we have part of this PV panel is being shaded, that will cause this condition, which is this one, like you see in this figure here. Okay, part of the panel is being shaded. So what does this mean? It means the current actually on these panels will be significantly reduced compared to these panels. And these panels will become like a load for the other cells. So this will result in becoming a load. It means all the current generated by other cells will significantly impact or will be dropped through these cells. And this is what happened when we have non-shaded cells, and this is what happened when we have shaded cells. This is the impact of power reduction current power reductions on the solar cells. But actually, what happens on the IV curve, when you have this kind of curve, so this is what will happen. So you have multi-peak. So the question is, which one is the MPP? Yeah, automatically this looks like the MPP, but now it's become challenging because you have another peak here, and you may have multi-peaks, maybe 3 or 4 or 5 peaks. So that's why we call them a local peak and a global peak. This is a global peak here, and this is another local peak. Okay, and this is some of the effects. What happened when we have this partial shading? These partial shadings will cause hotspots. Hotspots means actually this is actually damage of the solar cells due to the heat accumulated on the excuse me, accumulated on the cell. Okay, as we see just now, that's one of the cells becoming a load, and then all the power will drop, and the heat will be accumulated due to the high current, drop on the cells, and slowly the cell will be damaged. And this will be permanent damage, means the whole panel has to be changed. And this is just to show you the impact, how the PV cell under partial shading conditions. You can see after 1 second what happened, after 5 seconds, the heat will be loud, the heat starts picking up. This is one cell in one panel. You can see the heat, and then the heat will start be going through all the cells. So what I'm going to share with you today is one of the algorithms that we have done, which is the DE algorithm, which is used to track the maximum power, and then we compare its performance compared to other methods. So this is the full chunk of the algorithms. We start with initializations, mutations, crossover, selections, and terminations, and then the end. So this is the initializations, what happened. Okay, you select the 2 points, only 3 points are used, and we call the target vectors. And in the MPP systems, DE optimization algorithm is used to track the maximum. And then here, target vectors, we select x1 equal to 0.3, 0.6, and 0.9. And then the mutation, okay, multiply the difference between the 2 vectors with the mutation factor, which is f. Okay, here, and we normally choose f based between 0.4 to 0.8. Okay, but in our proposed systems, we select 0.6. And then the crossover, a random number, okay, which went following the normal distributions, is a rate between 0 and 1. And in this case, also we selected 0.67. Then the selection of the terminations is based on between the power is less than 1.5%. If the difference is power than 0.5%, then we do termination. And this is the proposed simulation. You can see here the number of PV panels, 1, 2, 3, 4. And this is our converter. Okay? And the output, this is the load here. And this is the V-in and the sensors to sense the voltage and current, and the controller. The controller is here. Just to simulate and see. And this is what happened. Actually, we did the comparison between one of the good methods, which is the P&O also. And we see the difference between the 2 methods. The first one, we created this partial shading condition, which is these 3 local MPPs, and then we have 1 global MPP, which is at 186, which is representing the highest power. And another pattern we created later, which is this pattern of partial shadings, and the maximum power on global MPP is 138 watts. Okay. If you look into this differential evolution algorithm, we can see the tracking. Okay, it happens, start tracking, the algorithm is trying to search, and then after that it tracks the MPP, which is 186. Okay, it's 186, which is correspond to this 186 here. You can see it takes a bit of time to reach to the steady state. Okay. However, the P&O algorithms, you can see it's faster actually reaching the steady state, but the problem is it does not track the MPP. it tracks much lower power compared to the DE. And this shows that the power, the voltage, and this is the current, and this is the duty cycle, how it changes. The duty cycle is trying to set till it reach to 0.3, and then it settles at 0.3, which is correspond to the NPP. Also, again, we change the partial shading pattern, which is here. And also we notice in this time the DE algorithm is faster and also able to track the maximum power, which is 138, compared to the P&O, which is also almost the same, 117. So this is just a simulation work. And then what we did the construction of the prototype, the hardware, which is the DC-DC converters, and then these two sensors, and then this is the microcontroller. Okay. And we do the experimental verifications of both, actually. We compare both the P&O and also the evaluation. We created this partial shading, okay, conditions. And this is the IV curve, and you can see the algorithms accurately detect the NPP, which is 99, the efficiency is around 99.5. Which correspond to 4.87 ampere and 57 open circuit voltage. And you can see the power is 184.46. However, the P&O, you can see, is tracking the wrong entity, which is here. And this is the voltage and current, and the efficiency is around 85. The difference is more than almost 15%, 14%, almost 14%. So this is in terms of tracking the entity. And this is the curve, how it looks like. So we zoom in, and then you see the power. You see the power. It takes around 0.64 seconds to track the entity. Whereas this, the P&O, it takes 0.8 seconds. It's much slower. All right. So again, we change the curve, the IV curve. You can see the curve, the power curve change. You see that's the DE actually accurately detects the MPP, whereas the P&O does not detect. So this is it's only 117. Well, this is 136 watt. It's much higher. Efficiency 98.7. This efficiency is 84.54. So it's much lower. So this is also in terms of speed of tracking. Yeah, you can see here the speed of tracking of the P&O is faster, 0.2, whereas the DE is much faster. So again, could you please mute? Everyone, could you please mute? Okay. Then we change the solar irradiance. Okay, there was a sudden change in the solar irradiance, and you can see there is a change in solar irradiance here. And then we check the maximum power, which is around 91 watts. Okay, whereas you see the P&O, when we do a sudden change in the irradiance, you can see the track, and then it takes some time to reach the MPP. So you see here from 137 it goes to 91 watt when it with solar irradiance change. Whereas this is goes to 174 watts, so it's a lot of difference, almost 20 watts difference. So again, we do another test, which is the load variation. We do a load variation. Yes.
So can you conclude here, because from 11 a.m. Our technical session will start.
Okay. Just 1 minute.
Okay, sir. Okay.
Okay, so we do a load variations from 300 ohms to 600 ohms and to 300 ohms again. We do the load variations, and you can see for the DE algorithms is accurately tracking the MPP compared to the DE. So as the conclusions, it's proven that the DE algorithm is actually providing a better tracking speed better performance in terms of even with the load variations, even with solar irradiance changes, and also with different partial shading patterns. So this is the end of presentations, and I open maybe for one or two questions before we end the session. Thank you.
If any question, kindly write to sir in chat box.
Maybe the audience was expecting different topics and talking about different topics. That's why there will be maybe no questions.
Good morning, sir. I have a question here.
Yes, please.
Sir, now the problem of partial shading or the hotspot creation can be overcome with a new bypass circuit. Now, rather than using a diode-based circuit, now the people are moving towards an MOSFET or IGBT-based. So, which one would be and prefer according to you?
Yeah, but actually there are a few methods actually which can be used into this avoiding the problem of partial shading, which affect the hotspots on the PV panels. The traditional way, yes, is the diodes, where we group a number of cells and then we put a bypass diode to minimize the impact. Yes, but there is a new research which is looking into voltage equalizers, okay, and how to balance the power between the cells using the MOSFET switching. Yes, that's. But still in the commercial one, it's still the diodes are the most commonly used one. Yeah.
Thank you, sir.
Okay, Ravindra. Hello.
Yes, sir. Sarwan sir, can you give the formal vote of thanks?
Yes, sir. Good morning, all. On behalf of 5th ICCCA Organizing Committee, it's my immense pleasure to thank our keynote speaker, Professor Sir McAuliffe, fellow IEEE, professor in electrical engineering. Sir, it was a great opportunity for the audience and participants to hear the advancements in the MPPT technique, and it was interesting when we are seeing the hardware results. It was and creating a spark in all the participants to work on the MPPT. Thank you so much, sir, for your valuable time. Thank you all.
Thank you. Thank you.